In previous lecture, we talk about another type of major applications, a main avenue of applications for hypergraph container methods to prove sparse random analog of some classical theorem, like Mantel's theorem and multicolor triangle Ramsey, the Shear's theorem, how they hold in a sparse random environment. We replace the ground set to the sparse random sets. So today we're going to see, today is likely to be the last lecture for container methods. We're going to see one more application, which is to use container method, a third type of sort of application, use container method for constructions. Okay. This is lecture 15. So let's begin with stating the most general form of hypergraph container theorem. So hypergraph container theorem. We need some preparation. Suppose we have a R uniform hypergraph. So here's the setup. We're given a R uniform hypergraph. For simplicity, I would just call it R graph. And let's say this given average, let D to be its average degree. Okay. Now we can define the codegree of subset of vertices as what you may imagine. Definition, codegree. If you have a set of vertices, given a set A of vertices of the hypergraph, R graph H, we write D of A to be the number of hyperedges in H containing number of hyperedges of H containing the set A. So in other words, this is the set of all edges in H such that this edge contains A as a subset. This set of edges, you take the cardinality. Now we can define the maximal J's codegree for all, which is the maximum codegree over all set of size J. Now this is called J's maximum codegree. where J, of course, range from 1 to R. We are in the R-uniform hypergraph. So for any J from 1 to R, we define J's maximum codegree to be denoted by delta J, which is the max over all dA, where A is of size J. No problem. Now, take a parameter tau. This is one more step. Take a parameter tau, which lies between 0 and 1. And then we're going to define some function. Define this function delta h tau. What is this guy? Just some 2 to the some constants depending on uniformity. -1, it's just some constant. Usually R is constant. So some constant times the sum of this term, the sum, when you take codegree for pairs all the way to codegree for everything, but codegree for everything is just 1. So you have J from 2 to R, delta J over the average degree of the hypergraph, D, times tau to the J minus 1. Maybe I should write slightly bigger. Tau J minus 1 times 2 to the some constant. This is again some constant because J is most R, which is constant. This is the function. Maybe I can move it here. Okay. Now, after defining this, we can now state the, let me give you some example. Let's consider only 3 uniform hypergraphs, which is what we will use today. So R is 3, you have 3 uniform hypergraph. What is this function? This function, let me simplify it for you, equals to 4 times maximum pair codegree, delta 2, divided by average degree times tau, plus some constant 2 times maximum triple codegree, which is just 1 actually. Every 3 vertices lies in at most 1 3 hyperedge, divided by d times tau squared. Okay. Now here comes the hypergraph container theorem. One of those versions. So we have an R-uniform hypergraph H. So we have a R graph. We given H is some R graph with average degree D. So let me just hidden this D here. And this is defined with this average degree of the hypergraph. It's hidden there. On vertex sets, on M vertices. Okay. On vertex set capital N. And now we take a constant. So here are the inputs. And we have constants epsilon and tau between 0 and 1/2. Suppose we satisfy, first of all, tau is at most some constant depending on the uniformity R. So in this case, 1/200 R times R factorial, and then you square the factorial, just some constant depending on R. And then suppose this function that we defined, codegree function, is at most, again, this some constant depending only on epsilon and uniformity R. So this is the bound. Usually, well, if you take epsilon to be a constant, everything here is a constant. So this is just saying that this is bounded by some constants, and tau is small. Now, what does that mean? If you look at this, or even you look at the simpler form, this is at most some constant, let's say 0.01. It just means that we don't have pairs lying in too many edges. We don't have triples all the way to R tuples lying in too many edges. It's an upper bound on the code maximum J's codegree, J's maximum codegree for every layer. So, which says basically roughly that the graph, the edges are smoothly distributed. You don't have any part that's particularly dense, because if you have any part particularly dense, then this part, the subset of vertices here, will have huge codegree, which is forbidden here. All right, so we have a hypergraph where the edges are smoothly uniformly distributed. Then we have a clustering phenomenon for the independent sets, meaning we have a collection of containers for its independent sets. Now, if this is true, then there exists a constant C, which is at most some constant depending only on the uniformity. So it's absolute constant, such that and a collection C, which is a collection of subset of vertex set of V, the containers, such that the following holds. First of all, they are containers for independent sets. For every independent set, I in H, there exists a container A in C, such that I is containing this container. Maybe let me change to C. Second of all, number of containers, there are not so many of them. Log of the container. So the number of containers at most 2 to the this constant, absolute constant C, times total number of vertices in our hypergraph capital N times tau times log 1 over epsilon log 1 over tau. So here a tiny remark is that this is usually lower order term, which grows, because epsilon and tau is something smaller than 1, so this is something bigger than 1. But because of the log, they are growing quite slowly. Actually, oftentimes epsilon is absolute constant, so you forget about it. Now, well, epsilon could be a function also, but because of log, it's lower order term. So this is lower order term. We want the number of containers to be S. So the number of containers is at most 2 to the roughly some up to log factor n times tau. To have fewer containers, to get better union bounds, for example, we want tau to be as small as possible. So to have fewer containers, want tau to be as small as possible. Okay? Because the number of containers is roughly 2 to the tau times n, up to some polylog factor. Polylog, blah, blah, blah. Okay? Right. So, but that doesn't mean that we can take tau to be as small as we want because of this constraint here on the codegree. So we want codegree to be not too, so for example, if you look at the 3 uniform case, you want these to be bounded by some absolute constant 0.01, for example. That puts a lower bound. If we can compute the codegree, that puts a lower bound on tau. Here, right? This is smaller than something. That means tau square must be bigger than something. So we have to solve these to find minimum. So get minimum tau satisfying this condition on the codegree. All right. Let's see maybe a example of how we get the containers for triangle free graphs. Remember, for triangle free graphs, let me remind you. Where did it go? Here. We have containers for triangle free graphs. Well, every triangle free graph is a subgraph of the container, and the number of containers is 2 to the n to the 3/2 up to polylog n. Okay, n to the 3/2. And each container is almost triangle free. So how do we get these from the general form? Basically, we're going to phrase a triangle free graph as some independent set in a hypergraph. So I think I mentioned this before. What we're going to do is we're going to construct this 3 uniform hypergraph. Container for triangle free graphs on N. So I will quickly go through this. I mentioned this before. What you're going to do is you construct H, which is the 3 uniform hypergraph, 3 graph, where the vertex sets are the edge set of Kn. Okay, and 3 vertices are the 3 edges forming the hyperedge. Say E1, E2, E3 form an edge in H. If and only if they form a triangle in Kn. All right. So in this case, an independent set here, I in H, what is it? It's a set of vertices, which is a set of edges of Kn. So it's a graph on M vertices, which does not have any hyperedges, no triangle, correspond to triangle free graphs. One-to-one correspondence to a triangle free graph on N. Okay. Now let's see why our bound on the number of containers here gets stuck at 2 to the n to the 3/2, some constant, times log n. All right. Basically, let's check this remark. We want tau to be as small as possible. In this case, what's capital N? Capital N vertex. In this case, capital N is n choose 2, roughly n squared. Let's forget about constants. So that means, and the number of containers is what? C in the hypergraph container is 2 to the some constant, capital N, which is n squared times tau, right? Times tau and some log factor. Log factor. So we want the minimum tau. And the minimum tau should satisfy what? This guy. The Hart inequality. That means we want this guy to be at most some constant. Take epsilon to be absolute constant. So Hart requires this guy to be less than, say, some absolute constant 0.001. Okay. Now, what is delta 2 and delta 3? Well, delta 3 is just 1. Simple. For any 3 vertices, there's at most one hyperedge if they form a triangle. If they don't form a triangle, there's no hyperedge containing them. Delta 2 is also at most 1. This is also easy. Why? If you have 2 vertices, E1, E2, well, if they look like this, it's possible that they contain in the triangle. If they vertex disjoint, they don't even have a triangle containing them. Easy. So this condition becomes what? Forget about this constant. This is basically constant now. 1 over d tau plus 1 over d tau squared. Tau goes to 0. So this term is larger. It's a stricter condition here. So what really matters is this part. Leading term. And this part, if you solve it, tau must be at least 1 over square root d. Yeah? But what is d, the average degree of this graph? Of this hypergraph? Look. Average degree for a vertex. What's a vertex? A vertex is a edge in Kn. For any vertex E in V of H, so here's E, which is in Kn. The degree is the number of triangles, right? Degree of E is the number of triangles in Kn containing E, which is precisely n minus 2. So it's n minus 2 regular, this hypergraph. Every triangle is a hyperedge. So we get that tau is at least tau is at least 1 over square root n. So here, this is at most, 2 to the n to the 3/2 log n constants. All right, some simple calculation, you can get that. Now, we're gonna use this general version of hypergraph container. In particular, just the 3 uniform version is enough for the next application, which is a geometric application to get a construction of a set of points, no 4 on the line, but is very rich in collinear triples. So next problem, Kurdish 4-3 problem. So the goal is want to find, here's the goal, find a set of points in the plane that sort of has two contradicting property, such that, well, on one hand, there's no 4 points on the line, no collinear 4 tuple. You don't have like dot, 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 dot. This is not allowed. Okay. Okay. No, no. You cannot have 4 points on the line, but you are very rich at many, rich in collinear triples. So what does this mean? That means if you take a sufficiently large subset of these point sets, you will get a collinear triple. So let's formulate this question formally. So given definition, let's first define points in general position. If we have a set of points A, set of points, is in general position in the plane is very simple. Just means there's no 3 points on the line, no collinear triple. If there is no 3 points on a line. Okay, so this is, let's say you have an easy way of getting general position is on the plane, you can just lie the points on the convex angle. So you have n points, no 3 on the line. So this is general position. This is good. And what about this? If you draw the grid, this is bad. You have, for example, 3 points on the line. Okay. Now we can define the function which measures the largest subset of points of a given point set that lies in general position. So for let alpha A to be the maximum size of A prime, where A prime is a subset of A in general position. Meaning no 3 points on the line. Find the largest subset of A of points, set of points, with no 3 points on the line. That's alpha A. Now we define alpha n to be the minimum over alpha A for all A of size n in the plane. And S A has no collinear for triple for tuple. Okay. In other words, alpha n is how large? In other words, i.e., How large? What is the largest? What is the largest subset of an endpoint set? Endpoint set in the plane with no collinear full tuple. That we can guarantee to find. Oops. What is the largest subset in general position? Of an endpoint set in the plane with no collinear full tuple that we can guarantee to find. Okay. Good. So it's this function. The current best bound, well, before the bound-Freddy proof, that alpha n was little o of n and little omega. So that means it's much larger than square root n log n. There's a huge gap between lower and upper bounds. So what does lower and upper bound means once again? Lower bound means no matter what a set of endpoints, no matter what a set of endpoints we are given, no matter what endpoints that we are given, we must have some way of finding, some algorithm of finding a subset of it of size much larger than square root n log n, such that they are in general position, given that this original set has no collinear full tuples. Okay. What does upper bound means? So the upper bound means construction, right? So this upper bound means a construction means you need to find some set of endpoints in the plane with no collinear full tuple, such that no matter how you choose a subset of this size, you guarantee to find collinear triple. Okay. Any questions about the notation? This notation is important. If you don't get the notation, you wouldn't follow the rest of the lecture. Okay. If there's no question, let's continue. First, as an exercise, let's try to prove some weaker lower bound. This exercise is not so hard. Prove the weaker lower bound that alpha n is at least some constant times square root n. So let's not prove n log n, square root n log n, prove square root log n. Here's a hint to show that n is at most alpha n plus alpha n choose 2. All right. If you can show this, you have the above bound. Good. So what's Furedi's original proof for the upper bound? So Furedi's idea for upper bound so he uses ideas use density Hell-Stewart theorem. Use density Hell-Stewart theorem for combinatorial lines. So what he did is he take a random projection of the combinatorial cube. 1, 2, well, let me write it like this. Of the cube, 3 to the n. Okay. This set obviously, this original set obviously has no 4 points on the line because this is a cube, hypercube, where in each direction you can only go 3 steps, right? So you don't have 4 points on the line, which has no collinear 4 tuple. Good. And why now what you need to show is any positive fraction of points will contain a linear triple. And this just basically the statement of density Hell-Stewart. So density Hell-Stewart DHJ says that for any positive fraction of this cube, you will contain a combinatorial line, which is 3 points on the line. Now, this collinear triple is preserved by projection. So that's it. This line contains 3 points. Okay. Right. Now, what we're going to do today is to improve these upper bounds to something polynomially smaller than n, than linear. So this is a recent development by Yusuf Bollock and Yusuf Shoimoshi. A nice breakthrough on this geometric problem using container. This is perhaps one of the first applications of hyperbola container theorem on geometric results in discrete geometry. So today we're going to prove theorem. This is by Yusuf Bollock and Yusuf Shoimoshi. They prove that when n is large, alpha n is at most n to the 5/6 plus little 1. So this is really a big improvement. Before, we only know it's just barely sublinear. There's no hope of proving anything that's n to the 0.99 using density Hell-Stewart. And so here, using container, we can go all the way down to 5/6. So still, it remains open. Still, there's a gap between roughly root n to the 5/6. If you can improve this power 1/2 or this power 5/6 by epsilon, by absolute constant c, that would be a very nice result, I think. So this is something, if you're interested, you can try to improve it. Okay. So what does this mean? What does this upper bound means? Let's translate it so that we know what we're trying to prove. So this means what we need to show a construction of an m-point planar set, an m-point set on the plane R2, such that it has no collinear four tuple, and for any subset of size much larger than n to the 5/6 plus little o1, then it contains a collinear triple. Okay, this is what we need to do. The idea is the following. This idea, at a very high level, but okay, let me first say the sketch of the proof, the idea. Is we take, consider an original structure, the starting structure, which is three-dimensional cube, discrete cube, 1 to m, so something like this. Oops, I don't want to draw it, so in this step, you have m points, and m points. So the discrete cube, length m on each direction. What's nice about this initial structure m cube is that it contains few collinear four tuple, but many collinear triple. It has few, the number of collinear triples is of order we will see later, magnitude m to the 6. But the number of collinear four tuple up to a polylog factor is also m to the 6, up to a polylog factor. So this, let me write tilde means up to a log m factor. It's also m to the 6. So they are roughly the same. Now, what's good about these is that, so there are many, let me emphasize, many collinear triple, but few collinear four tuple. What's good about this is that we can do a random sparsening. So this is the first step. Now we're going to do a random sparsening, random sampling, or sparsening. This just means we take a subset R in this cube where each point is taken, each point chosen with probability, roughly 1/m. So m to the m to the 1 plus little o 1. Or maybe 1 plus or minus little 1, whatever. Now, to do this sparsening, because this is triple and this is 4 tuple, when you sparsely take the sampling, this number will drop by different factor. Here will drop by p to the 3, right? For every triple. Here drop by p to the 4. So the number of 4 tuple, they are much, much fewer in the random set when your probability p goes to 0. Meaning that when you take small p, there are much, much fewer 4 tuple than 3 tuple and collinear ones. Then we can just do first moment deletion to remove a point from every collinear 4 tuple to kill all the collinear 4 tuples. Now we have the first property, right? Then you will have very few number of collinear 4 tuple is much less than the size of the set in expectation. The size of the random set R. Good. Wait, is it correct? Yes, right? Because what is the random set R? This is roughly m to the 2 plus little o 1. You multiply by 1 over m. What is this? This is like this times p to the 4. This is roughly m to the 6 times p to the 4. It's also m to the 2 plus little o 1. So if you're careful with this plus little o 1, this is a lower order term. Then you can remove a point. First moment deletion. From each collinear 4 tuple, you will get your final set R prime, where this R prime satisfies these. So all we need to prove is that this R prime still retains many, many of these collinear triples, so that if you take a large subset of that, we still have one collinear triple surviving there. All right. And alpha R prime is at most. So R prime is roughly what size? This is roughly m to the 2 plus little 1, right? We want to show alpha R prime. That means the largest subset of R prime with no collinear 4 triple is roughly m to the 5 over 3 plus little 1. So if you set this guy to be n, this is roughly n to the 5 over 6 plus little 1. That's the bound we want to prove. Any questions so far with the outline? So the outline has 2 steps, which is we've seen constructions of 2 types usually. Either it's structured, highly structured. For example, algebraic constructions for C4 free graph, C6 free graph, and C10 free graphs, right? Or norm graph. This kind of algebraic construction, very highly structured. Or we have something purely random construction for diagonal range in lower bound, for example. And in the past 1 decade, there are many hybrid of these two form that perform much better than random construction, which is meaning that initially you start with something very structured. Then you do some random substructure of that, random sampling. Combining, you'll do better. For example, here, in this example, we start with some initial structure that's already sort of good for us. It has few collinear four tuple, but many collinear triple. It has some nice property favoring our purpose. Then we do random sparsity. Another example, for example, is 3-color diagonal Ramsey lower bound construction. Half algebraic, half random. It performed better than purely random. Also, Boris book's construction, random algebraic construction, you have some, can be viewed somehow along this line. Right, so this is some comments. Okay. So just for technicality, we are actually working in the 3-dimensional space. What we need at the end is a planar set in R2. So the final step is we have the set with the property that we want, but instead in R3. All we need to do is to take a generic projection, take a random projection toward onto some, say, hyperplane going through the origin. I'll leave it as an exercise to show, for you to show. So exercise, final step is so here's the exercise for this final step. Suppose we have a set of points in R3. So we have a set of points, W, set of points, finite set of points. Maybe let's call it P. Oops. If you take an orthogonal projection of P onto some random hyperplane through the origin, on a uniform random hyperplane, through the origin, then, given these two, the collinear triples are preserved. So for any in general position, that means not on the line. In P, we have the projection, the probability that their projection from a line is 0. This just basically means if you have a desired set in 3 dimensions projected, you get a desired set in 2 dimensions. Okay. Let me mention some key steps we need to invoke the 3-dimension to invoke the hypergraph container to get this construction, get this idea to work. What are the key things we need? Well, let's do some basic calculation to let's do the simple calculation here. Compute the number of collinear triples and 4 tuples in this 3-dimensional cube. Let's do the simple one, the lower bound first. There are at least m to the 6 many collinear 4 tuples and triples in M3. So warm up. So fact. At least some constant m to the 6 collinear triples and collinear 4 tuples in m to the cube. Actually, let me write it as a lemma. Okay, let's do this. Proof. Why is this easy? Well, how do we get many collinear triples and collinear 4 tuples? Basically, you can just do this. Let's grab, let's say, this is of length m, right? Let's grab, let's say, cube, a 1/4 subcube. So this is half, this is 1/4, good. Inside here, in this m/4 cube, inside this cube, so this is m/3 cube. Inside this smaller red cube, if you pick any 2 starting points, and then you use this starting point to step 1 more step or 2 more step, you get collinear triple or collinear 4 tuple, right? You will never step out of the box because your step length is smaller than m/4. If you make 2 furthermore steps, you remain in this box. And the number of ways to choose these 2 initial points is the square of the size of this. So you get m to the 6. So let's write it down. A collinear 3 or 4 tuple can be written as x plus y, x plus 2y, or maybe x plus 3y, right? If you want 4 tuple. That means every one of these collinear 3 or 4 tuple is, we just need to pick x, y in here, then all these points lies inside here. Okay. That's it. Any question? The upper bound slightly harder. Let's skip it for now and finish the rest of the proof and come back to the upper bound. All right. So it's not much more than what we proved. Okay. Before deriving the main thing, we still need a supersaturation to invoke. So we know that the whole cube contains m to the 6 many collinear triples. So what sort of supersaturation we need? Well, we have to first phrase a set in general position. A set in general position means no 3 points on the line as some independent sets in some hypergraph. A natural choice would be, if you want to phrase how to define hypergraph H, we would like to phrase set in general position as independent sets in this hypergraph H. So the natural choice would be the vertex set is just the set of points if you have n points, right? Now the edge set, so this is a 3-uniform hypergraph. Edges are all collinear triples. So it's a 3-uniform hypergraph, 3 graph. What's an independent set? Independent set is a subset of the point set. It's a subset with no hyperedges, no collinear triples. That means they are in linear position, general position. So we make the correspondence if you consider this hypergraph. Okay. So for this hypergraph, we need supersaturation so that we can iteratively invoke this container theorem. And the supersaturation means if you take a not so small subset of the point sets, still there are many edges. If you take everything, if you take the whole vertex set, which is m cube, actually I'll just take m cube. If you take everything, we do have many hyperedges, m to the 6. Now what we need is, if you take a large subset of that, still we have many hyperedges. So we need supersaturation so that we can iteratively iterate the hypergraph container theorem later to get small containers. Okay, which is important. What does that mean? Supersaturation. This is the following theorem. Lemma. Supersaturation. For any set A, subset of the cube, M cube, with size at least 100 times M squared, then the number of hyperedges induced on A, this just means the number of collinear triples in A. Is at least some constants, absolute constant C times A cube over M to the 6. If you let M to be of size M cube, A to be of size M cube, oh, sorry, I made a mistake. It should be 4. If you let M to be of size M cube, A to the 4 is M to the 12. This is M to the 12 if A is everything. So if you have everything, M12 over M6 is M6, which is what we just proved above. We need it to be true all the way down to any set of size M squared. Still, we have many collinear triples. This is the supersaturation. Okay. The supersaturation is not very hard, but again, let's skip it for now and try to finish the rest of the proof. Assume this supersaturation. Okay. Right. So let's finish the rest of the proof, assuming supersaturation. Now we can prove that alpha n is at most n to the 5 over 6 plus little o1. So as I said, we're going to consider the 3 uniform hypergraph H on vertex set M to the cube, where the hyperedges are all collinear triples as above. Now we're going to iteratively apply hypergraph container theorem. What does it mean, iteratively apply? This means we're going to iteratively of small containers for independent sets. So, and then we can use union bound to prove. You use first moment deletion, you do sparsening, then first moment deletion to get rid of collinear 4 triple, and then 4 tuple, and then union bound using these containers to prove that large subset contains collinear triple. And what do I mean by small? And what do we mean by iterative? That just means initially you have some hypergraph, you have hypergraph H. In the first application, first round, you will get some containers, let's say C0 containers, which is, for example, C1, C01 maybe, C02, C0, I don't know, T, whatever, okay? Now if this container is small, we don't do anything. Let's say CJ0 is small, meaning the size of this container is smaller than n to the, how large is small? 8/3, I think, plus little 1. Then plus some maybe let me use epsilon, delta. Did I use delta before? Okay, let's use gamma. Gamma is small. Then we stop. We don't do anything with leave it as it is. But if the container is large, that means larger than this, okay? Larger than this, we can then use supersaturation to know that the induced hypergraph on this container still has many edges, okay? Large average degree. Then for this new hypergraph, we apply container theorem again. This is what we mean by iteration. Apply again hypergraph container to the subhypergraph H induced on CJ0. Okay. So what we need to show is that, well, this process must stop. You cannot go forever. The number, so this is what we mean by rounds. In each round, you apply hypergraph containers for every one of these. We will show that actually the number of rounds that we go is at most some constant times 1/gamma, where gamma is the absolute constant, which is sufficiently small. So the number of iteration, number of rounds is big O of 1/gamma. So need to show the number of rounds is big O of 1/gamma, which is a constant. Okay. So let's parameterize things. Suppose we have some container at some stage. Let's say suppose we are at round I. At the ith round, we have some container. Cij at the jth container in the ith round. Its size, let H ji to be the induced subgraph on this container. And let's suppose its number of vertices here, which is the size of the container, is parameterized by n to the 3 minus beta. Okay. So what I said earlier is that initially, there's no container. We just apply to the whole hypergraph. Beta is 0. Now, if beta is bigger than 1/3 minus gamma, then CJI is small, right? It is at most n to the 8/3 plus gamma, which is small. We stop. We don't do anything with the container. Otherwise, we apply hypergraph container to this hypergraph, HJI. Now let's compute its average degree. So now let's consider this HJI hypergraph. The number of edges of this hypergraph by supersaturation. This is supersaturation. Oops. Is at least, what does it say? A to the 4 over m to the 6, right? Is at least n to the 3 minus beta to the 4, the size of this set to the 4 over m to the 6. I should write m here. Did I? Maybe this, everything is m. Okay. M to the 6 times some constants. So this is roughly some constants, m to the 6 minus 4 beta. Okay. And this implies that the average degree, so we have the average degree D is at least constant 6 to the 4 beta over the number of vertices. The number of vertices is m to the 3 minus beta, right? So this you get m to the 3 minus 3 beta. This is the average degree. Now for 3 uniform version, let's copy paste the hypergraph container. Where is it? Now, for 3 uniform hypergraph, what we need to care about is this guy, right? So what is delta 2 and delta 3? Let's compute. Delta 2, well, delta 3 is 1. This is easy because it's 3 uniform. What's delta 2? Delta 2 means for any 2 points, how many hyperedges containing? Hyperedges are all the collinear triples. And this is trivially m, because every line through this cube of size m is at most some linear in m, many points, m step. So it's less than equal to m. Good. So as I said, we want to take, so here we're going to take, let me tell you the choice of tau and epsilon. We're not going to take epsilon to be small anymore, to be constant anymore. We want to take epsilon small so that, oh, I forgot to write the third one. I made a mistake. Right. There's a third property I didn't write. which is each container is almost independent sets. So let me write here. For every independent sets, for every container, the number of edges induced on the container is at most epsilon fraction. Okay. And that's important. Why this is important? Because if we take epsilon to be small, okay, remember, we want our iteration to be small. How do we make sure that the number of iteration is small? We want to show that after every round, this container is shrinking quickly. So every time the container size m to the 3 minus beta for some beta, we want it to, after 1 over gamma rounds, shrink all the way down to this size. And why this is shrinking? If we can take epsilon to be linear, to be polynomial, some constant time polynomial in M, then every time the container, the number of edges it induced is shrinking polynomially. But by supersaturation, we know that every polynomially large set m squared above has many, many edges. If this is shrinking, that means necessarily this container C is also shrinking polynomially. That means after bounding number of steps, it shrink all the way down to the desired size we want. Okay? Let me write it down. We're going to take our epsilon to be polynomial and m to the beta minus, let me tell you what it is, 1 over 3 plus gamma over 2. Okay? In particular, this is smaller than m to the negative gamma over 2. Because we know beta is less than 1/3 minus gamma, right? As beta is less than 1/3 minus gamma. Otherwise, we are done already. So epsilon is small, and we're going to take tau to be m to the beta minus 4 over 3, as small as possible so that this holds. Right? Let's check. So what you want is delta 2. So checking this, delta 2 is m over average degree d, which is m to the 3 minus 3 beta, plus delta 3 is 1, m to the 3 minus 3 beta, times tau times tau square. Sorry, wait, let me write d tau. Well, okay, first of all, this is m. Oh, let's write it. M over d tau plus 1 over d tau square. It's not clear which one. So this to be less than some absolute constant. Let me just write 1. So that means we need both of these to be less than 1. And that requires tau to be bigger than d over m. And also bigger than 1 over square root d. tau bigger than m over d, sorry. M over d. Okay, you need to be bigger than these two. When you need to be bigger than that two, you just set them to be equal. That's usually the best. So you set this to be equal, you will get can you set it to be equal? No, probably not. Let's compute it. So the first term is what? M over, what's d? M to the 3 minus 3 beta. M to the 3 beta minus 2. The other one is 3 minus 3 beta is M 3 beta minus 3 over 2. Which one is larger? Why it doesn't look like anyone, folks? 1 second. Let me see. Delta 2 is m, that's correct. Delta 3 is 1. So m over d delta plus 1 over d, m over d tau plus 1 over d tau square. You want tau to be bigger than m over d and tau to be bigger than 1 over root d. Okay, so maybe there's some other inequality to optimize here when we try to do this iteration. So I will leave it as exercise for you to check these details, why this choice of tau in this calculation is optimal. So when you choose this tau, now what happens is, after some calculation, this is calculation, calculation. What we get is we get a collection of 2 to the some constant 1 over gamma times n to the 5 over 3 log n squared containers. Each of size and most n to the 8 over 3 plus gamma, the size where we stop. Good. Now we're going to do, this is the container for the hypergraph H. Now we do sparsening. To random set R, where we take the probability P to be 1 over m times log square root log m, for example. Then you can compute expected size of R is MQP, which is much larger than the expected size of the collinear triples, 4 tuples in R. What is this? This equals to, for every 4 tuple, probability P to the 4, linearity of expectation, surviving in R, times the number of collinear 4 tuples, we mentioned it, is at most m to the 6 times log m. Okay, we didn't prove it, but let's assume it. This you can show that it's much bigger. So first moment deletion, you get R prime, no collinear for tuple, and R prime is at least R over 2. Finally, you just need to prove that alpha R prime is at most m to the 5/3 plus gamma. Okay. We just need to show there is no independent sets of size m to the 5/3 plus gamma in R prime. Independent set is a set of points in general position, right? So this corresponds to need to show with probability tending to 0, no independent sets of size let's say k, which is this m to the 5/3 plus gamma, is contained in R prime. This, you just use the first moment again. So the expected number of independent sets of size k in R is what? At most, the number of containers and each container has size m to the 8/3 plus gamma. Choose k. This is the total number of size k independent sets, right? Okay, and for this to survive in R prime, you need to multiply by p to the m, p to the k. And this can be shown tends to 0. That means they use Markov or whatever, there's no independent set of that size in R prime, meaning this exactly. Any question? So I skipped some of the details like supersaturation. Maybe I'll mention it next week. Maybe I'll just skip it. You can refer to the original paper. But the main idea is to iteratively apply hypergraph container to get not so many containers, each one of which is small. And then using better union bounds from the container theorem, you can get the construction that you want. This key idea is you start with something that's nice, and you do a sparsening to make it even nicer to the one we want. All right. So that concludes most of the things I want to talk about container theorem. So next week, maybe we fill in the details for this supersaturation lemma here, and then we will move on to the next method. Okay. See you guys next week if you have no question. Thanks for listening.